Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. I appreciate you joining us here today as we are talking about a new type of application problem that can be solved with a system. We've already talked about some fairly straightforward, simple problems, and we've begun to look for problems that students tend to say are more challenging. In our last unit, we talked about digit and coin problems, or I should say in our last lesson, we talked about digit and coin problems. Today and tomorrow, we're going to look at distance problems. And then we're going to follow that up with work problems here in a few days. And then we might get around to doing a lesson on investment problems before trying to tie it all together in my classroom. You'll notice today we do have a theme. We're going with a Wizard of Oz theme, so hopefully we can see some examples of how the characters from the Wizard of Oz might benefit from understanding how to solve a system. Here's a pretty good example. It says, while searching for Dorothy, the Wicked Witch and her flying monkeys reach a fork in the yellow brick road. They decide to split up. The witch decides to go east and moves about 80 miles per hour on her broomstick. The flying monkeys fly west, but only fly 72 miles per hour. And how many hours will they be 760 miles apart? Part of the reason that distance problems become so challenging for students is there's a lot of information given to you, a lot of numbers, a lot of facts, and it's very difficult to organize those in your head. So what I would recommend doing is whenever you're given a distance problem, just take a minute and draw yourself a quick sketch of the story, and that's going to kind of help guide you through what's going on. I think you'll find that to be very useful. So Dorothy, while searching for Dorothy, the Wicked Witch and her flying monkeys reach a fork in the yellow brick road and decide to split up. The witch decides to go east and moves at 80 miles per hour on her broomstick. So I've just sketched east to the right because that's how it tends to appear on most maps. The flying monkeys then fly west, but only fly at 72 miles per hour. In how many hours will they be 760 miles apart? You'll notice I labeled this as step 0, draw a picture, because we did have a 4-step plan for solving systems of linear equations when they were in application problems. So I wanted to make sure that I didn't mess up that 4-step plan. We added this in as a 0. Notice that we do have one other piece of information here, and that is that the total distance apart is 760 miles. We want to know how many hours it will take until they are 760 miles apart. Since the number of hours is our unknown, we would label that as our time. Now, at this point, it's important that we take a moment and stop and think about what we have. We have monkeys that are moving at 72 miles per hour and a witch that is moving at 80 miles per hour. That is an example of a rate of speed. We're given a distance of 760 miles per hour, and we're asked about time. So, when we begin to look for relationships and we think about rates of speed, distances, and times, that should bring up an idea that we talked about much earlier in the year. Do you remember what that is? And of course, that is the distance relationship or distance problems, because we learned that the distance is equal to the rate of speed times the time. If that formula is unfamiliar to you, you might want to go back and review distance formulas from earlier in the year when you're dealing with a single person or a single object moving. In this case, you'll notice that I've set up the witch's distance. And I've written distance equals rate times time. Now notice this is D1, R1, and T1 because I know I'm going to need a distance, rate, and time for the witch, and I'm also going to have to go back later and find a distance, rate, and time for our flying monkeys. In this problem, if we start looking for these pieces of information, you will notice that we do not know the witch's distance. There is a distance given to us over here on the far right, 760 miles, but that is the total distance between the witch and the monkey. We don't actually know the witch's distance. We do know her rate of speed, which is 80 miles per hour. We do not know how much time how much time it's going to take for them to become 760 miles apart. So I'm going to leave that blank. If I think about the flying monkey's distance, they would have their own distance, rate, and time equation. Notice I put D2, R2, and T2 because we don't necessarily know if our distance, rates, and times that we're going to use over here are the same distance, rate, and time we used over here for the which. Do we know how far the monkeys fly? We do not. Do we know how fast the monkeys fly? We do know that. Do we know how long the monkeys fly? We do not. Now notice I switched from T1 and T2 to just T's. The reason for that is there's nothing in the problem to indicate that the monkeys and the witch are flying for different amounts of time. Since they're both starting in opposite directions at the same time, we know they'll be traveling for the same amount of time until they reach the 760. Hopefully these two equations separately are not surprising or new to you. You may not have thought of them at first because we've not done distance problems in a very long time, but this is going to be the key to working with the problems we have today. It's just like the distance problems before, but there is something else we want to make sure we talk about. And that is this idea of total distance traveled. Notice we don't know the witch's distance, we don't know the monkey's distance, but we know that together they've traveled 760 miles. They were together, one moves one way, the other moves another way. I probably need to talk about that just a little bit. When two objects are moving in opposite directions from one another, the distance between them is always the sum of their individual distances. If you have this on paper, I would probably go ahead and circle or underline or highlight that word always. If they're moving opposite directions, the distance between them is the sum of their individual distances. And I can give you a quick example of that. If I were to walk 7 miles in one direction, and you were to start at the same point and walk 5 miles in the other direction, our distance is going to be 12 miles apart because I've gone 7 to the right, you've gone 7 to the left. The comparison would be 5 plus 7 to get from one to the other. Because of that, I'm going to create a third distance equation that says my total distance, d sub t, is equal to distance 1 combined with distance 2. Or if I know how far the witch has traveled and I know how far the flying monkeys have traveled, I can combine those to find out how far apart they are. In this case, we know a few pieces of information. We know the total distance traveled. That's up here. That was the 760 miles. We don't know the distance the witch traveled, but we do have an expression that represents that. We don't know the distance the monkey traveled, or the flying monkeys traveled, but we do have an expression that represents that. Notice you have 1, 2, 3 equations in this system. We can either solve this by substitution or by linear combination, which is also referred to as the addition method or the elimination method. I'm going to use substitution, so I'm going to take this d1 equals ADT, and I'm going to put it in here. I'm going to put the ADT in instead of the d1. I'm going to come over here. If D2 is the same as 72t, I'm going to replace this D2 with that 72t. And there again, I already know the total. Using substitution, notice I changed D1 to red so it matched. I changed D2 to blue so it matched, but it's the same exact equation. I put the 760 in for my total distance. That was given to us in the problem. I put ADT in because I'm substituting from this equation. I put 72t in because I'm substituting from this equation. Notice you now have a single variable equation using t that we can solve. ADT in 72t is 152t. Property of equality to divide away the 152. and you get a time of 5. Since our question was to find how many hours it would take until they were 760 miles apart, we would answer the question, they will be 760 miles apart in 5 hours. If we can get in the habit of thinking like this and using the substitution method, this is not overly complex to solve. Now, sometimes we'll know the rate but won't know the time. Sometimes we'll know the time but we won't know the rate. Sometimes the monkeys and the witch might be going in different directions. Those are the kind of things that make each problem interesting or unique. But by and large, this idea of two separate distance equations and then some form of an equation that relates those two will be used. By the way, this equation right here, distance total equals distance 1 plus distance 2, when I do my substitution, you'll notice that I do come up with this equation right here. Total distance equals rate 1 times time 1 and rate 2 times time 2. As we get better at these, we can begin to stop writing out the picture or drawing out the picture. We'll eventually stop doing these separately, and eventually we'll do this all in one single step. But breaking down our thinking, I think, is going to be helpful for us, especially early on. There again, my students tend to want to skip over drawing the picture, but what they find is without the picture, they tend to make a lot more errors, and most of the time they'll go back and start doing that. Let's try another one of these. The Wicked Witch of the East and the Wicked Witch of the West decide to meet for tea. This was, of course, before Dorothy dropped a house on one of them. When they finish, they travel in opposite directions for 2 hours, headed for home. They're now 68 miles apart. If the Wicked Witch of the East travels 2 miles per hour faster than the Wicked Witch of the West, how fast is each one of them traveling? Here again, I would start off by drawing my picture. I have one witch going to the east. I have one witch going to the west. And I know I'm trying to find out when they're 68 miles apart. The variable in this problem is asking if the Wicked Witch of the East travels 2 miles per hour faster than the Wicked Witch of the West, how fast is each traveling? Notice that the word each means I'm going to be solving for two different things. I'm going to be solving for the Wicked Witch of the West's speed, and I'm going to be solving for the Wicked Witch of the East's speed. Now, in the other types of systems, we defined these as maybe X and Y or R and S, but I find it's going to be useful since we're using a distance equals rate times time equation to use R1 and R2. These are two separate rates of speed. Now, when I begin looking for relationships, here's what I find. I have a West Witch and an East Witch, and I have a distance equals rate times time equation. I don't know the distance the Wicked Witch of the West travels. I don't know her speed. But I do know that they're going to travel for 2 hours. That's right here. They both travel for 2 hours. Notice I wrote R. I probably should have left that as R1. Over here on the right, I don't know the Wicked Witch of the East's distance. I don't know the Wicked Witch of the East's speed, but I do know that she's going 2 miles per hour faster than the Wicked Witch of the West. Notice that if the Wicked Witch of the West is going R or R1, instead of keeping this as R2, I went ahead and rewrote it as R plus 2. Now this might be a little bit of a cheat on my part. Notice down here I've said R2 is the East Witch's speed, but then I wrote it's equals R plus 2. Technically I'm using substitution here, where I'm replacing that R2 with the R plus 2. I do know the Wicked Witch of the East's time. Two separate equations, one for the West Witch, one for the East Witch, and then of course my total distance is the sum of their two distances because they're going in opposite directions. Now, I don't actually know their distances, so I'm going to have to use substitution. Do I know the total distance? Well, sure, that's right here at 68. Do I know distance 1? No, but I do have an expression that represents it. Do I know distance 2? No, but distance 2 is the same as 2 times r plus 2. So I can take that original equation, notice I brought it over here to the left and I've cleverly rewrote it using color coding. I'm going to replace distance 1 with 2r. I'm going to replace distance 2 with 2 times r plus 2 by using the substitution method. Notice I also plugged in my 68 because that was given to me. I have the problem written out in a single variable, so I'm just going to use a little computation. Distribute your 2, combine your like terms, subtract using the property of equality, divide away the 4 using the property of equality, and you get r is 16. Now, if my west witch, or my R1, is 16, R2 is R plus 2, which is 18. The Wicked Witch of the East is going 2 miles per hour faster than the Wicked Witch of the West. Make sure we answer the question. The Wicked Witch of the West flies 16, the Wicked Witch of the East flies 15, and yes, I am aware that's a typo. That is the homophone witch, which happens to sound like witch. Must be a little bit of an autocorrect in there someplace. You see how this is really the same basic structure as the previous problem? We've got 3 equations in our system. We then go through and plug in the values that are equivalent, and then we can solve very quickly. I do think this gets a little trickier because you've got to watch out because we're moving different speeds. That's why I put it second, but it is something you want to be aware of. Doesn't change the basic structure of the problem, just means we need to slow down and be cautious. Once again, if you look at this step, you do have your total distance equals rate times time plus rate times time. You'll see this come out over and over again. The Emerald City and the Witch's Castle are 96 miles apart. The Wizard's balloon is flying through the sky at 18 miles per hour towards the Witch's Castle. The witch is flying her broomstick from her castle toward the Emerald City at 14 miles per hour. In how many hours will they meet? Once again, I'm going to suggest drawing a picture. I'm not writing it out this time. You have a wizard at his Emerald City going to see the witch. You have the witch going from her castle to see the wizard. And you want to find out, and you know they're 96 miles apart. The question is, in how many hours will they meet? Since that is our question, that is our unknown, and we define our variable. There again, I'm not listing the steps anymore because hopefully you're becoming familiar enough with those. Once we've done those three things, we start looking for relationships. I can see this as a distance problem, so I'm going to start trying to create a distance equation for both people. I don't know the witch's distance. I do know that she is moving 14 miles per hour, and I don't know how much time has passed. Notice I've converted that to just t because they're both flying for the same amount of time. I do not know the wizard's distance. I do know he's flying 18 miles an hour, and I do know he's flying for the exact same amount that the witch flies. I can look at these and see these two people are moving in opposite directions, so the total distance they cover is going to be the sum of the distances they've traveled. So if in order to cover 96 miles and meet, maybe she went 90 and he went 6, maybe she went 80 and he went 16, maybe she went 70 and he went 26. Either way, whatever these are, they have to add up to 96 miles. I would recommend pausing and trying to finish this on your own if you think you can. I'm going to keep going with the assumption that you have already done that, and I'm just going to walk through this very quickly because this is the third time we've done this. There again, here's my total distance formula. Once again, I have color-coded it so you can see what's going on. I substituted in the values that were equal to those distances. Remember, those are rates and times, rates and times. It is a single variable equation now. Combine your like terms, divide away the 32, and the time is 3. Make sure you answer the question. They will meet in 3 hours. After a while, they do start to all seem the same, particularly if the times are the same and the times are not different like they were in the last example. That can sometimes make people struggle. Once again, at this point, this is a distance equals rate times time plus rate times time equation. Now this one's a little different. Dorothy and Toto see a tornado quickly approaching. Toto takes off running for the farmhouse at 65 feet per second. Dorothy is not as quick and can only manage 55 feet per second. After how many seconds will they be 45 feet apart? Now I mentioned that this was a very different problem. Do you know why? Notice that Dorothy and Toto both see the tornado approaching. They both head towards the house. That means when I go to draw the picture, Toto runs toward the house, and Dorothy also runs toward the house. Notice that my graphics are getting less fancy as we go along. That's because the graphics are there to entertain you, but I certainly would not expect you to do fancy artwork on your work. I would just expect that you would be drawing something simple enough to organize your thoughts. If they're going the same direction, that will change a few things, but we're going to hold off on that for a second. Let's go ahead and point out that we're solving for the time. We have our picture drawn, we have our variable identified, and now we're going to start looking for relationships. We know the total distance apart is going to be 45 feet, and we know each of these people or characters are going to have a distance equals rate times time equation. I'd recommend pausing and see if you can figure out Toto's on your own. I'm going to head and go on. Toto's distance is unknown. We do know he's moving at 65 feet per second, and we do know his time is in seconds. Notice that t has now just become a t because we know that Dorothy and Toto are both moving for the same amount of time. Can you pause and figure out Dorothy's equation? Dorothy's distance is equal to her rate of speed, and she moves the same amount of time as Toto. We have two equations for our system. What we don't have is an equation for the total distance because they are no longer moving in opposite directions. Instead, they're moving in the same direction. So we have a new equation here. The distance apart is equal to d1 minus d2. When two objects are moving in the same direction, the distance between them is always the difference between their individual distances. And here's an illustration of that. If you ran 7 miles one direction, and I ran 5 miles in the same direction, I would be here, you would be here, and the difference would be 2 miles. We would be 2 miles apart. Anytime you go in the same direction, the distance apart is a subtraction problem. In this case, your solution is 2 miles. Knowing this, we can take these two equations along with our distance apart equation, and we can begin to use substitution to solve the problem. Notice once again, I've color-coded it for you. The distance apart is given to us. It's 45 feet. I've taken D1, which is Toto, and replaced it with his information. I've taken D2, which is Dorothy, and I've replaced it with her information. And now you have a single variable equation that you can solve. Notice that they will be 45 feet apart in 4.5 seconds. Now, some people often ask me, how do I know that Toto is D1 and Dorothy is D2? Couldn't Dorothy be D1 and Toto be D2? Yes, they could, but if you look down here, if you did that, what you would end up with is instead of 65t minus 55t, you would have 55 minus 65, which would give you negative 10. and you divide both sides by -10 and get -4.5. You see, that's a little bit confusing for people to interpret what -4.5 means. It kind of goes to who arrives first. Here we're saying that if you're comparing Toto to Dorothy, Toto is 4.5 feet, or in 4.5 seconds, he will be that. I can't even explain that. Let's back that up just a little bit. We'd end up with a negative number. The negative number has to do with who arrives there first. And no, that's not it either. I'm going to just edit this out, and I'm going to keep on going. Notice that the distance apart equals rate times time minus rate times time. Very similar to the equation we were using before, but you can see that right here. Last example. Dorothy has just been captured by the Wicked Witch, leaving the Tin Man, the Scarecrow, and the Cowardly Lion behind. The Tin Man and the Scarecrow begin walking 2 miles per hour through the haunted forest to find her. Upon summoning his courage, which takes him an hour, the Cowardly Lion races along at 3 miles per hour to catch up. How long will it take him to catch up to the others? I'm going to start off defining my variable and drawing my picture. Notice we have the Tin Man and the Scarecrow going for their walk, and we have the Cowardly Lion coming up behind them. Both of them are going to need a distance equation. I don't know the distance that the Scarecrow and the Tin Man travel. I do know how fast they are going. And notice what I've used for my time. My variable is defined as the time the lion runs. But the lion started an hour later than everybody else. Since he started an hour later and he is T, they have walked all the hours he walked and 1 minute more. This is a little bit tricky. When we look at the Cowardly Lion's distance, it is unknown. We know that he's in a hurry trying to catch up, so he goes 3 miles per hour, and we've defined the time as how long it takes him. Since they're moving in the same direction, this is a subtraction problem, we want to know when he catches up. So what's the distance apart we're looking for if he catches up? Well, that would make the distance apart a 0. We don't want them to be apart at all. We want him to catch up. I then go through and replace D1 with the expression that's equal to it. I replace D2 with the expression that's equal to it, and I color-coded that to make it less confusing. And now you have an equation in T that you can solve. And you end up with T equaling 2. He will catch up in 2 hours. I will tell you that most people tell me when the times are different, that's when they struggle the most. You have to be careful when defining your variable so you know which variable is T and which variable is an expression written in T. Now, if I were doing this in a very detailed manner, I could call this 2t1 and call this 3 times t2, and then somewhere I could say that t1 equals t2 minus 1 or t2 plus. I could come up with some kind of way to make this an extra substitution step, but I think that makes it more confusing rather than less confusing. Hopefully, after seeing these two types moving in the same direction and moving in different directions, you'll find that these will be a lot easier for you. Please do not underestimate the value of starting off with your picture and writing each distance equation separately first. I think you're going to find that to be much, much easier. As always, I hope you found this useful. If you like this, please make sure you smash that like button for us so that we know you are following along and it's been valuable. Make sure you leave us a comment in the comment section, turn on those notifications so that you don't miss any of our upcoming resources. As always, I wish you all the very best. Until the next time, take care. Until the next time, take care.